Hello everyone, welcome to the ECE573 Advanced Embedded Logic Design Lab. So in the previous video, we discussed about how to set up the interrupt in the Zinc SoC or Microblaze processor, and now uh, we'll briefly discuss the code before moving to the interrupt handler or ISR writing. So, as we discuss the 6 steps of the interrupt handling, okay. So here I have added the desired .h file as for the timer, for the experimented.h file, exception.h file. This is for the AXI interrupt, and this is for the, if we are using the Xilinx printf statement, this is .h file will be needed. So here I'm mentioning among the AXI timer whether I'm using the timer 0 or timer 1, and here I am mentioning what is the reset value. So after the timer is counting, say counting up from 0 to 255, it will go back to 5 and then it will start counting from 5 onwards. Okay, so this is the reset value of the counter, and this is my interrupt handler or ISR, which we'll discuss it at the end of the video. So these are the function definition. Okay, so you can see that in the int main function, I'm defining the two structure. For the one is for the AXI timer, and the second is for the AXI GIC. Okay, interrupt controller. Here I have not used the GPIO, but you can always add the GPIO as well. Then, as we discussed, the first thing is to do the initialization of your timer as well as the interrupt using the corresponding initialize function in the respective .h file. The IDs will be available in the experimented.h file. Then we discussed we need to initialize the exception handling logic inside the core. So via this function, then we need to interconnect the master exception handler inside the core with the GIC. So you can see that the this is my interrupt handler, which is the Xilinx provided interrupt handler for the AXI interrupt hand GIC, and this is the GIC instance. So I am connecting it with the master interrupt handler inside the core. So once this has happened, now what we are going to do inside our GIC, we are going to tell the GIC that from where you will get the interrupt, then what to do after you receive the interrupt. So you can see that this is the peripheral from where this is the structure for my GIC, and this is the peripheral from where I'm going to receive the interrupt. If from this peripheral, I'm talking about the interrupt with this ID, and once the interrupt comes, I need to perform this function, that is the ISR, which we need to write. Okay, and then next step is to use the enable function, so that on the GIC side you close the switch between the GIC and the peripheral. Then you do the same thing, you close the switch at the output of your mode, okay, your peripheral. Once you do that, then you need to do the last step, which is the enabling the exception. Okay, so this is these are the process you need to follow. Then the last thing which you need to do is that you need to connect your handler. We have now only informed the GIC that what is my handler for the corresponding peripheral, but we also need to close the link between my timer structure and the corresponding handler. So we are telling the timer that whenever you generate the interrupt, this function will be executed. Okay, so these are the steps we need to follow. After that, it's a regular timer utilization where we set the option inside the timer. Okay, you need to enable the interrupt mode inside the timer, and again the auto reload. So auto reload, so it's a up counter. Then set reset value and start. So what I am doing is that I am writing the while loop, okay, and I'm just checking that how many times the interrupt has happened, and if the interrupt has happened 3 times, okay, then I'm stopping the timer and I'm disabling the corresponding interrupt, okay. And what I'm doing inside the interrupt handler, I'm just checking whether the corresponding interrupt has expired. If it is expired, I'm incrementing this function. So if this variable reaches 3, then I know that I have generated the interrupt 3 times. And once the interrupt has generated 3 times, I'm going to stop the timer so that the no more interrupt will be generated. I am just for the display purpose. Okay, this part I'll discuss it sometime later. I'm just taking the current value of the timer. I'm displaying it on the screen. Okay, so this part I'll come back in the few minutes. So up to this point we have discussed. We need to discuss this part and this part. So first is to discuss this first is to discuss this one and then this one. So ISR, that is the interrupt handling routine. So an interrupt handler or the ISR is the function that will be called, okay, when the interrupt occurs. Okay, for example, we have seen that this is the function will be called when the interrupt happens from that particular peripheral. There are few guidelines. We need to make sure that we keep the ISR as short and as simple as possible, because such ISRs will be executed only when the corresponding interrupt happens. And it's very difficult to debug these codes because these are executed not all the time. These are executed only when the certain conditions are met. Okay. So you need to make sure that these are simple and as short as possible. Then when these functions you should not spend a lot of time in this function. Whenever interrupt happens, your ISR's execution should come completed as quickly as possible so that you go back to your user code. So you should not write a very complex ISR one. Instead, what you should do is that you should generate some flags, internal variable, and these flags you can use in your main code to do some other additional task. Okay, so instead of doing all the task inside the ISR, you should just generate some flags or indicated value. These values you can use it in the your main code to execute the other remaining task. Okay. Also, many times it happens that when you go inside the ISR, you will disable the interrupt so that you don't get disturbed by the new interrupt. But make sure that when you are leaving the ISR, you enable the interrupt. That's a mistake we do many times, that we disable the interrupt, but we don't enable it. So that needs to be taken care. Okay. Another thing is that your interrupt may be generated by the multiple sources, or in some cases you may use the same ISR for multiple sources of the interrupt. Then how to distinguish that, okay, who has generated this interrupt at the particular time? Okay, that is one thing you need to make sure. And also you need to make sure that you are processing the interrupt for the right peripheral. Okay, so basically you need to make sure that whatever you are doing in the ISR is you are doing it for the right peripheral. Okay, so these issues may happen when you write one ISR for the different peripherals, or you may have the inside the one peripheral you have the multiple interrupt sources and you write a same ISR. So how to distinguish from which point it is coming from? So for that you need to take care of the additional precaution. One thing is that you need to check the status of the interrupt in the corresponding IP, that okay, when I come to the ISR, I'll go to that IP and check the interrupt register. In that register, if it is set, then I know that okay, this interrupt has been generated. So this is the one way. But to do this one, you need to know that you need to get the details about the IP who has generated the interrupt. So for this, Xilinx in their code has used the callback reference. Okay. So if you see your interrupt handling handler, you can see that you are along when you generate the interrupt, you also pass this callback reference, and this will tell you who has generated the interrupt. Okay. So when you are writing the interrupt handling routine, you should make use of this facility to identify who has generated the interrupt. Okay. So the Xilinx interrupt handler, which is we have used in the our interrupt handling logic, calls the application handler, that is your ISR, and it also passes the information about the driver instance, okay, which is relevant to the peripheral that generated the interrupt for that. Okay. So your the interrupt handler inside your core, which is the master interrupt handler, will call your ISR and will send this value. Okay. And this value can be used. uh, this is not the this why this is needed. So you can see that why I need to pass this value. Can't I use my original structure which I have defined for the timer? But you need to understand that that original structure which you have defined for the timer is in the main code, which is outside the scope of this handler. Handler is a separate function. Okay. So the original timer structure is not within the scope of the interrupt handler. So that's why you need a local version. And by using this callback reference, you can create your local structure of the time. And now you can see that this local structure and your original structure in the main, they are exactly same. They are pointing to the same IP. So whatever you make the changes using this local structure will also be applicable to that the original structure. Okay. So the instance timer AXI local, which you have created using the callback reference, is now the exact copy of the one in the main function, and the timer can be controlled in the same way as before. So even in the inside the ISR, you can change the timer from up to down. Okay, that is also possible because now you have the structure which has the all the information. Any changes to the local timer will also apply to the original copy of the AXI because they are linked together using a pointer. Okay. So these are the this callback reference is very important to identify the source of the interrupt, and you can use the source of the interrupt to decide the whether the to read and write from the particular registers inside the IP. So you can use this callback reference to ensure that the timer really did generate this interrupt. For example, there is a function called as whether the is expired, like timer control is expired. So you can use this value. If this value is 0, then you know that the or it is equal to 255. You know that the corresponding timer has expired. Okay, so the corresponding the functionality can be achieved. And then you can also clear the interrupt, disable the interrupt. There are multiple functions are there in the each IP. You can make use of this function. Now with this information, we'll go back to our the handler code. Okay, so you can see that this is the handler code which will be called whenever the interrupt occurs. And you can see that you are sending this callback reference. This becomes your local one, and then you are checking the whether this has been expired. Okay, if it is expired, you are incrementing the corresponding number of times the interrupt has happened by 1. And when this reaches 3, you are stopping the corresponding interrupt. Okay, so this completes the writing the interrupt as well as the interrupt service routine. You can write your own interrupts as per your functionality you want. Now the second thing I want to discuss is the display messages. Now if you see here in our block diagram, so suppose that I want to display the current value of my timer. Okay, I have read the values of the timer. You can see the value 1 which we use in the previous lab, and I want to display this on the uh, uh, I want to display it on in the simulation 1. Okay, so what are the options I have? I can pass this value to the GPIO and I can display using the dollar display or dollar monitor command. I can display it on the screen. Second option is that I can use this AXI light. Okay, so you can see the sorry, AXI UART. So what happens in the AXI UART? Whenever you use the printf statement, that printf statement will be converted into the AXI transaction and it will be passed to this UART IP, and this UART IP will transmit into the bits, will create a UART packet and will be transmitted on the UART port. This is useful when we are using the actual board. So what we have done in the today's lab, we have shared one test bench with you. And this test bench, what it does, it receives these bits and converts into the message and display that message on the screen. Okay, so you don't need to worry about this to understand this in more detail. But if you use the test bench, you can display something using the printf statement, and that can be printed on the TCL window of your Vivado screen. Okay, so for example, here if you see, we have created one character buffer. Okay, so suppose this is the timer stop value. I'm converting into the stream. Okay, and then this I am printing it here, and you will see that this value, timer stop value, will be printed on the TCL console. Okay, so now I'll show you the demo how it works. Okay, so now you can see the screen here. I have added the UART light and I have added the test bench which I have shared with you. Make sure that in the test bench these names are matching with your block diagram name, and the name of this wrapper is matching in your instantiation. Then I'll run the simulation. So after I run the simulation, once I run it for the sufficiently long time, you will see that the corresponding timer value will be displayed on the here TCL screen window at the bottom. Okay, so first thing what I'll do is that I'll add some counter value so that we can verify the values. So this is my counter, and I can see that the counter value, and then I'll also add the interrupt. So the timer interrupt. Okay, and I'll run it for say 3 milliseconds. So you can see after 3 interrupts are generated, my counter stopped working. And now you can see that this is my values of my count. Okay, my timer has stopped working. So this is the value of the count, 244. And you can see that now the data is being received over the UART in this received buffer in that Verilog code, and it takes time. Okay, so now if you see here, you can see that the data is being received. First you have received 2, then you will receive 4, and then you will receive another 4. Okay, so you have received 4. Okay, so now you have received the 4. Okay, and after some time you will see that the corresponding display will be there here. The 244 will be displayed here. So it takes time, but at least whenever, suppose you want to find out the time it took to execute the particular algorithm on the Microblaze and the time it took to run the particular algorithm on the here on the FPGA, and then you can get those two count values, and then you can display it on the screen. So here you can see that the 244 values they display on the screen. So this is the one way, and now I'll show you the another way of doing the same thing. Okay. Okay, so this is the previous lab where we have used the AXI timer and the GPIO, and we were displaying some values on the GPIO, and we are reading the AXI timer value. Now here you can see that what I have done, I have just made a small change in the test bench. I have added this monitor signal. So this monitor signal will display the values on this GPIO 4 bits whenever it changes its value. Okay. So now what I'll do, I'll run the simulation like the same thing which we did in the previous case, and now you will see that inside the TCL console window, you will see the display messages indicating the different values of the GPIO 4 bits. So you can calculate the timer values for the both the timer values, and you can use the discrete write to write those in the GPIO, and your test bench can display those values inside the TCL console. So you don't need to look at the corresponding timing waveform to know these values. Okay, so let's run it for say 3 microseconds. So you can see that the GPIO 1, GPIO 2, you can see that the values are getting displayed. Okay, so in this way you can get the display message working on this one, and this is usually useful for displaying your uh, displaying the corresponding execution time for the processor as well as the FPGA implementation. So this completes the today's lab. So you need to replicate all these things, and then you need to submit the homework.